Welcome to Chapter 2 of the Hartman Polaritonic Matter Framework. In this chapter, we dive into the concept of multi-flavor polariton fields and their pivotal role as the control substrate for programmable matter and advanced propulsion systems. Each flavor here refers to a distinct polariton species, such as polarization, exciton type, or cavity mode. By engineering the interactions between these flavors, we can precisely control the nonlinear dynamics, coherence, and momentum structure of the system. This foundational layer is essential for the operation of next-generation lenticular flying saucer propulsion, setting the stage for how we manipulate matter and energy at the quantum level. At the heart of multi-flavor polaritonic fields lies the Spinor-Gross-Pitaevsky equation, a powerful mathematical tool for describing the evolution of these quantum fields. This equation incorporates flavor-specific masses, nonlinear interaction coefficients, and coherent coupling term. By solving the Spinor GPE, we can predict how each polariton flavor evolves over time, how they interact with one another, and how external fields or potentials influence their dynamics. This formalism is crucial for designing systems where precise control over quantum states and their interactions is required. Let's formalize the multi-flavor polariton field mathematically. The field is represented as a spinor, psi RT equals psi 1 RT, psi 2 RT, psi 3 RT, where each psi j is a complex wave function for a specific flavor. Each component has its own density, Nj equals Ci2 and phase CIRJ. The effective mass Mj times for each flavor determines how it responds to external forces and interacts with other flavors. This mathematical structure is the backbone of the system's dynamic behavior. The Spinor-Gross-Pitaevsky equation governs the time evolution of each polariton flavor. It includes kinetic energy, potential energy, nonlinear interactions, coherent couplings, and external pump terms. This comprehensive equation allows us to model the rich dynamics of multi-flavor polariton systems, capturing both their quantum coherence and their macroscopic behaviors. To keep track of the various components in the multi-flavor polariton field, let's review the key symbols and their meanings. Psi j represents the wave function for flavor j, Nj is the density, Twar j is the phase, Mj times is the effective mass, Gjk is the nonlinear interaction coefficient, Jj is the coherent coupling, Fj is the pump term, Jj is the current density, and Ppol is the total polariton momentum. Understanding these variables is essential for interpreting the mathematical and physical structure of the system. The flow of polaritons within the material is described by the current density Jj for each flavor. This current is determined by the phase gradient and density of the corresponding wave function. The total polariton momentum density, Ppol, is the sum of the momentum contributions from all flavors. These quantities are not just mathematical abstractions. They directly influence how the material responds to external forces and how it can be used for propulsion. The Chapter 2 schematic visually ties together the mathematical and physical aspects of multi-flavor polariton fields. It features three wave functions entering a cavity, phase distributions above the cavity, zones of coherent mixing and nonlinear overlays, and holographic dispersion rings. These elements are not just artistic, they correspond directly to the underlying equations and physical processes described in this chapter. Multi-flavor polariton fields are not just theoretical constructs, they form the control layer for the lenticular flying saucer's propulsion system. By shaping polariton flows, engineers can manipulate internal stresses and momentum density within the craft's hull. Coupling terms allow for rapid regime switching, while nonlinearities tune the stiffness and inertia of the material. These mechanisms are foundational for the advanced propulsion and maneuvering capabilities described in later chapters. The field control layer, defined by the multi-flavor polariton fields, acts as the interface between the quantum dynamics of the material and the macroscopic forces required for propulsion. By adjusting the parameters of the Spinor GPE, operators can fine-tune the flow of energy and momentum throughout the hull, enabling precise control over thrust, stability, and response to environmental changes. The journey from multi-flavor polariton fields to actual propulsion involves several key steps. First, the fields are engineered to create specific phase and density distributions. These, in turn, generate internal currents and momentum densities. By channeling these flows within the hull, the system can produce net thrust or stabilize the craft against external disturbances. This seamless integration of quantum field theory and engineering is what sets the lenticular flying saucer apart. To visualize the internal dynamics, field lines are used to represent the streamlines of polariton current for each flavor. These lines trace the flow of energy and momentum within the hull, highlighting regions of circulation, stabilization, and net propulsion. By analyzing these patterns, engineers can optimize the design and operation of the propulsion system for maximum efficiency and responsiveness. The mathematical connection between polariton fields and propulsion is made explicit through the definition of polariton current and momentum. For each flavor, the current density Jj is given by the phase gradient and density, while the total momentum density ppol is the sum over all flavors. These quantities are integrated over the hull surface to determine the net force and thrust generated by the system. Within the hull, field lines can form closed loops, which are associated with circulating modes that stabilize the structure and shape its inertia. Alternatively, directed arcs across the hull represent net momentum flows that drive propulsion. By controlling the configuration of these field lines, the system can switch between stabilization and thrust modes as needed. The multi-flavor polariton field architecture is deeply integrated with the hull materials of the lenticular flying saucer. By embedding these fields within a polariton lattice composite, the system can dynamically adjust its mechanical and electromagnetic properties. This integration is what enables the craft to perform rapid regime switching and adapt to changing operational demands. At its core, the multi-flavor polariton field serves as the control substrate for programmable matter. By manipulating the parameters of each flavor, operators can program the material to exhibit specific behaviors, such as changing stiffness, optical properties, or even its phase. This level of control is unprecedented in material science and opens the door to a new era of adaptive, intelligent structures. Non-linear interaction coefficients, JGAC and coherent coupling terms. JGAC are the knobs that allow for fine-tuned control over the system's behavior. By adjusting these parameters, the system can transition between different operational regimes, such as from a stable, inertial mode to a high-thrust propulsion mode. This flexibility is crucial for the multi-mission capabilities of advanced craft. External pump fields, FEA, provide the energy required to sustain and manipulate the polariton fields. By modulating these pumps, operators can inject energy into specific flavors, initiate transitions, or maintain coherence across the system. This external control is essential for real-time operation and adaptation to changing mission requirements. Phase distributions above the cavity and holographic dispersion rings are key visual and functional elements in the multi-flavor polariton field architecture. These features represent the spatial variation of phase and the dispersion of energy within the system. By engineering these patterns, the system can achieve precise control over wave propagation, interference, and energy localization. The Chapter 2 schematic is rendered in a cinematic cutaway style, featuring engraved authorship by James Hartman and the year 2026. This visual approach not only highlights the technical details, but also pays homage to the pioneering work behind the framework. The cinematic style helps convey the complexity and elegance of the multi-flavor polariton field architecture. Chapter 2 sits at a critical juncture in the Hartman Polaritonic matter framework. It builds on the foundational physics established in Chapter 1 and sets the stage for the matter writing and propulsion mechanisms detailed in Chapters 4 and 7. Understanding the control physics here is essential for grasping how the entire system operates, from programmable matter to advanced propulsion. Chapter 1 of the framework lays the groundwork by defining the physical substrate of polaritonic matter. It explains how different regimes such as frozen, light, and liquid light are achieved in microcavities and extended structures. This foundational knowledge is crucial for understanding the advanced control mechanisms introduced in Chapter 2. This chapter focuses on the control layer, where spinor, polariton fields, couplings, and nonlinearities are used to shape momentum, inertia, and stress patterns within the hull. Mastery of this layer is what enables the sophisticated behaviors and performance of the lenticular flying saucer. Looking ahead, Chapter 4 introduces the matter writing engine, which uses shock wave to solid nucleation to flash form custom phases in the hull and internal structures. This process is made possible by the programmable control, established in Chapter 2, highlighting the interconnectedness of the framework. Chapter 7 is where the multi-flavor polariton fields become the active engine of the lenticular flying saucer. The hull is realized as a polariton lattice composite, enabling quasi-particle-particle switching and anisotropic polariton flows for thrust and maneuvering. The groundwork laid in Chapter 2 is essential for understanding the advanced propulsion mechanisms detailed here. The polariton field lines in the schematic act, much like electromagnetic field lines, tracing the flow of current and momentum within the hull. These lines are not just visual aids. They represent real, measurable quantities that determine how the craft moves and responds to external forces. By studying these patterns, engineers can optimize propulsion and stability. To calculate the total effect of polariton momentum on the craft, the momentum density is integrated over the hull surface. This integration yields the net force and thrust, which can be further modulated by the spatial distribution of the polariton fields. Such calculations are vital for designing efficient propulsion systems. The conversion of polariton momentum into mechanical thrust is described by the phenomenological thrust coupling term. This term encodes how the internal momentum of the polariton fields is transferred to the hull and ultimately to the surrounding environment, producing motion. Understanding and optimizing this coupling is key to achieving high-performance propulsion. By configuring the polariton field lines into closed loops or directed arcs, the system can switch between stabilization and propulsion modes. Closed loops help maintain structural integrity and resist external disturbances, while directed arcs generate net thrust for movement. This dual capability is a hallmark of the multi-flavor polariton field architecture. The ability to dynamically control the properties of the hull, such as stiffness, inertia, and response to external forces, is made possible by the programmable nature of the multi-flavor polariton fields. By adjusting the parameters in real time, the system can adapt to changing conditions and mission requirements, ensuring optimal performance at all times. One of the most remarkable aspects of the HARTMAN Polaritonic Matter Framework is its seamless connection between quantum field dynamics and macroscopic engineering. The multi-flavor polariton fields operate at the quantum level, but their effects are manifested in the large-scale behavior of the craft. This quantum to macroscopic link is what enables the revolutionary capabilities of programmable matter and advanced propulsion. In summary, Chapter 2 formalizes the use of multi-flavor polariton fields as the control substrate for programmable matter and propulsion. By mastering the Spiner-Grosspietovsky equation, flavor dynamics, and field line structures, engineers can design materials and systems with unprecedented control over their properties and behaviors. This chapter is the bridge between foundational physics and practical engineering in the HARTMAN framework. With the multi-flavor polariton field architecture established, the next chapter will explore additional schematic representations and possibly introduce blueprint overlays. These visual tools will further clarify the complex interactions and design principles at play, preparing us for the advanced matter writing and propulsion mechanisms to come. The principles outlined in Chapter 2 have profound implications for engineering. By leveraging multi-flavor polariton fields, designers can create materials and devices that are not only programmable, but also capable of adapting to their environment in real time. This adaptability is key for future aerospace, defense, and materials science applications. Let's recap the key equations from this chapter: the Spiner-Grosspietovsky equation for each flavor, the definition of current density, and the formula for total momentum density. These equations form the mathematical backbone of the multi-flavor polariton field architecture and are essential for both theoretical analysis and practical design. The cinematic cutaway schematic style used in this chapter provides a visually engaging way to understand the complex architecture of multi-flavor polariton fields. By combining color-coded wave functions, coupling zones, nonlinear overlays, and holographic rings, the schematic brings the mathematical formalism to life and aids in both teaching and design. This chapter, authored by James Hartman in 2026, represents a significant milestone in the development of programmable matter and advanced propulsion systems. The engraved authorship on the schematic is a testament to the pioneering work and vision that underpin the Hartman Polaritonic matter framework. To conclude, the multi-flavor polariton field architecture described in Chapter 2 is the foundation for both programmable matter and advanced propulsion in the Hartman framework. By mastering the interplay of quantum fields, nonlinearities, and coherent couplings, engineers can unlock new frontiers in material science and aerospace technology. With the multi-flavor polariton field architecture firmly established, the next step is to explore its practical implementation in matter writing and propulsion systems. Stay tuned as we move into Chapter 3, where we'll delve deeper into schematic representations and prepare for the engineering challenges ahead. Let's review some key terms from this chapter. Polariton, flavor, spinor, Gross-Pitaevsky equation, nonlinear interaction, coherent coupling, current density, momentum density, programmable matter, and thrust coupling. Familiarity with these terms will help you navigate the advanced concepts introduced throughout the Hartman framework. The concepts introduced in Chapter 2 are at the cutting edge of material science and propulsion technology. By harnessing the power of multi-flavor polariton fields, we are paving the way for a new generation of adaptive, intelligent, and highly efficient vehicles. The future of propulsion is quantum, programmable, and limited only by our imagination.